everybody, this is David, and welcome to part 4 of the 7-step processor series. This is part 4, of course, and we're going to cover the control unit and instruction set. Alright, at the end of the last video, we ended up right here. We have the control unit here on the left, and the entire processor on the right. And so far we've built the main memory, which is the RAM on the right, the ALU, and then we've built two parts of the control unit up at the top, the clock and the stepper. One major change, I did change the stepper. It used to be a state machine. I also added a reset functionality, and honestly, let's go back and look. You'll see that step 7 of the stepper, it just goes right back in and resets it back to step 1. So you're going from step 6, and once you get into step 7, it's an immediate reaction back to step 1. So we really don't need a step 6. Oops, that's the way I meant to go. But you can see we don't need a step 7. I just changed this into a shift register, kind of like a counter. When it gets to when the bit that we want lit, when we get to step 6, basically on the next clock we want to go back to step 1. Otherwise we just shift that bit right, and that's it. It's essentially the stepper now is a shift register. And okay, so first thing you got to do is model it based on the schematics, right? And what I did, you can do it any way you want. This is how I did it. I begin at the top left of the schematic, and I work my way from top down and left to right. And any gates I come on, if they're OR gates, I use a capital O and I start numbering them. If they're AND gates, I use capital A and I start numbering them. Same thing with the NOT gates. You'll notice N1 right here where my pointer's pointing at. And you just label all the logic gates. And so in our Verilog code, we're going to need to label these wires. Well, if you just label the AND gates, or all the gates, with capital letters, then you can label the wires with lowercase, because Verilog is case sensitive, right? If you're using VHDL, you can't do that, because capital letter, it's case insensitive, right? Capital letters, lowercase letters, the same thing in VHDL, but in Verilog you can make it different. So if you make your gates with capital letters, you can make the wires coming out of those gates with lowercase letters. Then you can always track the signals, right? So just looking at down here, I'm using Verilog primitives for all the gates. So this is an example of how I modeled gate A5 right here in the lower left, coming out of decoder 1, right? The name of the gate is capital A5. The output wire is lowercase a5. So this wire is, this wire coming out into O1 is A5. And then, just every other, here's O9 coming out down here, which also goes into A5. I hope you get the picture on this. The numbers they're in hex. So if you notice, I got A1D, A1E, A1F. I counted hex, but I started at 1. And then here's something that you can replace down here. This is you can replace this with a NAND gate. You can see it's an AND followed by a NOT. I left it alone, but it's something that you can do, just a change in this. And there's a couple other changes I made that I'll talk about later. Alright, let's talk about the architecture of the control unit a little bit. You'll see on the left hand side we have the all enables. As you'll notice, the clock generation at the bottom, we have clock E, and it comes down on the left side for all the enables, clock S. That signal goes on top over the stepper and down on the right side. So these are all sets with an AND gate on each one. Enables are enabled only during clock E time. And you can notice the clock down here. Remember, we have clock E is like the 75%, clock S is the 25% right in the middle. So we're going to enable a register and then set it into another location. Sets are only enabled during clock S. One CPU component enables its output to the data bus, and one CPU component sets that data at its input. The stepper and the instruction register determine which CPU components to enable and set during a clock cycle. And we'll get more into the instruction set in a minute. but that's what goes in this instruction register down here at the bottom. All right, and the basics of the control unit is, it's like the clock is the drum beat that makes things go, right? It's what drives the stepper. Clock E and S facilitate the movement of register contents from one to another, and the stepper provides a series of bits that come on one after another every clock cycle. The control unit facilitates the fetch, decode, execute processor instruction cycle. I don't know if you've ever heard of fetch, decode, execute. That's basically what processors do in a kind of a conceptual kind of way. We'll talk about that more as we go along. The first 3 steps of the stepper are considered as the fetch part of an instruction cycle, where the next instruction is fetched from memory and put into the instruction register, and the remaining steps 4, 5, and 6 are the decode and execute parts of the instruction cycle. This is the instruction set for this control unit. These are the instructions, and these are the only instructions that this processor can process, and it does it through the control unit, right? The control unit is the conductor. It's what drives the processor to do these instructions based on the instructions in the instruction register, right? And executing simple instructions like these over and over in specific sequences at a very high rate of speed is essentially all that CPUs do. Of course, some CPUs have much larger instruction sets. They can do a lot more things. This is a very simple one, and this is basically all it can do. The control unit provides a way for the CPU to do one thing at one time and another thing the next time. The control unit needs an instruction to tell it what to do each time. The instruction set provides the instructions that this processor is capable of processing. A program written for this processor utilizes the instructions in this instruction set up here. Okay, now I'm going to start getting into the instruction set and some instructions, but I need to cover this bus 1 first because it's involved in the fetch process of the control unit. And you notice on the processor diagram here on the right, this bus 1 right here, and this is essentially what it is. And all it simply does is when we drive the signal to bus 1, then we want an 8-bit output that is essentially binary 1. And if it's 0, if the input is 0, then whatever is on the in will propagate through these gates to the out. So here's the fetch part of the instruction cycle. This is what happens during steps 1, 2, and 3. This is a basic rendition of the control unit, taking out all the other confusing stuff and just focusing on what happens in steps 1, 2, and 3. So in step 1, if you look following from the stepper coming down, we are enabling bus 1. It's on the enable side, right? Enable is on the left, set's on the right. So we are enabling bus 1. We are also enabling the instruction address register. And at the same time, we are setting the memory address register, and we are setting the accumulator. So what's happening here is that we are enabling the instruction address in the instruction address register and setting it into the memory address register. We are addressing memory for the next instruction. And then what the bus 1 does in capturing the ALU result is that the opcode of the ALU, if we go back to right here, you'll notice at the bottom left these 3 AND gates that are driving the ALU. They are tied to this wire step 5. Follow step 5 coming all the way down to these AND gates. They are only enabled during step 5. So any other case of an instruction in the control unit other than step 5, we will have 000, which is an opcode for add. So essentially we're enabling bus 1 to add 1 to the instruction address to set up for the next instruction. Okay, now in step 2, and you'll see more of this. I got more examples of this coming up. Step 2, we enable RAM. So in step 1, we've addressed RAM. In step 2, we're going to enable the contents in that address out into the data bus and set that in the instruction register. And then step 3, we're going to take the value that was in the ACC, which is the address +1, and set it into the instruction address register for the next instruction cycle. And this is just an example ALU instruction. So after you fetch, now we're in steps 1, 2, 3. Now we're going to decode and execute. This is an example of an add operation, and this is actually backwards, but don't worry about it. Just look what happens here. So step 4, we enable a register and we set it into the temp. So this operand B is R1. So we are enabling that into the temp register. Then in step 5, we are enabling R0, which is where we have operand A, and we are setting the accumulator. So through step 4, we have operand B in the temp register driving operand B of the ALU. And then on the next step, in step 5, we're enabling R0 to be at operand A of the ALU. The opcode, of course, is 000, like I just said. And, well, it would be driven anyway in step 5 in an ALU instruction, but it's 000. This is add. And we capture the addition between operand A and B in the accumulator. We set that down in here. And then in step 6, we take and we enable the accumulator value, that value that we just captured, the ALU result, and we put it back into R0. But actually the way it works is it goes back into R1, and I'll show you that in a minute. And so here's another example of what you could do after we did the ALU instruction. You can take that value that's in R0 and store it in memory. And so what would happen is on the next instruction, after it fetches that instruction through steps 1, 2, 3, now in step 4, we will enable R2, which is the address, and set it into the memory address register. And then in step 5, we will take that ALU result, that is R0, and set it into the RAM. And we just stored the previous computation from the ALU in RAM. This is just an example. Now we're going to go through some what actually happens, and we're going to start with the ALU instructions. So this is where we break down the instruction set, right? We have 8 bits to work with. So every instruction we have 8 bits, and each of those bits has a particular meaning, right? And in this processor, the very first bit, right over here on the left, if it's a 1, it's an ALU instruction. Plain and simple. If it's a 1, it's an ALU instruction. If it's a 0, it's a non-ALU instruction, and I'll cover those in a minute. Let's go through the ALU instructions first. You can see that the next 3 bits represent the opcode. We have 8 different instructions in the ALU, so we have 8 different operations, 8 different ordering of bits that we can put right here for the opcode. Then the next 2 bits is what designates what register A of the operation is, and the last 2 bits designate register B for the operation, which is what it says up here. Now, in this box in the middle is important. So for a 1 input operation, such as a shift left, a shift right, or a not, right, only operates on operand A, the value in register A will go through the ALU, and the result will be put in register B. For 2 input operations, such as add, and, or, it's also XOR, the values in reg A and reg B will be sent to the ALU. They will both go to the ALU, right? Reg B will be put in the temp, and then reg A will be put, and then we drive the opcode, and the result will be put back into register B. So as an example down here, this we have an example instruction, which is 1011 0110. So if we look at the first one, yep, it's an ALU instruction. The opcode 011 is a NOT, and then we are using register 2 and register 1 for reg A and 2 for reg B. So what this instruction will do, it will NOT the contents of R1 and put the result in R2. Now here's an example of a 2 input, 101. So 101 is an OR operation. We are involving register 2 and register 3. So this will OR the contents of register 2 and register 3 and put the result in register 3. It's important to understand what registers and where the data goes, where it comes from, and after the instructions. And this explains it all right here. So here is basically, okay, this is programming language for all of the ALU operations, right? We have the opcode or the instruction, and then the 2 registers involved in the operation. Now here's an example, or this is what happens with the registers in an ALU operation, right? So reg B is enabled, and we set that into the temp register. And then in step 5, well, that was step 4. Step 5, we enable reg A, and then set the accumulator, and then we enable the accumulator and set it back into reg B. And this is just a basic breakout of how the registers and react with other signals in the instruction, and how the decoders are used for addressing the registers. Right? Now, here is, we will get into more ALU operations. So yeah, this is basically what happens. This is a breakout of it. Right, steps 1, 2, and 3 is the fetch. It's the same for every instruction. It does the same thing. So fetch, and then so now steps 4, 5, and 6 depend on what ALU instruction we have. And so, right, like we said, look at step 4. Reg B is enabled, and then we set the temp register. Also notice that the first bit in the instruction register is also involved in this, enabling this AND gate here with step 4, because that designates this as an ALU instruction, right? If this first bit is a 1. So now we enable this. Now in step 5, we have the first bit of the instruction register is enabled. Also step 5 enables these AND gates to drive the opcode, which is instruction bit 1, 2, and 3. They will go drive the ALU. And then in step 5, we are enabling reg A and setting the accumulator. And then this little piece down here, which I said you could replace with a NAND gate. This only comes into play when we use a compare operation. If you notice over here on the top right, compare operation is 1, 1, 1, which is the only time that this AND gate is enabled, which is the only time that this NOT gate will be disabled, and we will disable this AND gate. So for a compare operation, if you remember, we don't care about the result. We're only using the compare operation to set flags. Therefore, if for a compare operation in step 6, this AND gate is disabled, and we are not enabling the ACC and setting it into reg B. For every other ALU operation, though, we are. This NOT gate is enabled. This AND gate here is enabled, and so we take the previous operation in step 5 that was set into the ACC, and we enable it and put it into reg B. I hope this is making sense. And so now we get into load and store instructions. So these are all non-ALU instructions now, right? So for a load, if we're either or store, we're moving a byte of RAM between, or moving a byte of information between RAM and a register. If it is a load operation, and you can see the opcode over here, load is 000, which will activate this 3x8 decoder. Remember, from the control unit, we have this 3x8 decoder, and this is essentially for all non-ALU operations. Because if you remember, the first bit of the instruction register, if it's a 1, we have an ALU operation, which will come up, and this NOT gate, which is NOT gate N1, will disable anything that comes out of this decoder. Now, if we have a non-ALU instruction, which means we have a 0 here, this NOT gate will enable any of these outputs from the decoder. So this 3x8 decoder is only used in non-ALU instructions, and we have 8 non-ALU instructions because we have 8 outputs from the decoder. So instruction 000 is a load instruction. So we want to load from a register and put it into RAM. So if you look at step 4 for 000 coming out of the decoder, we have this AND gate up here. Step 4, we are going to enable reg A and put it in the memory address register. Because if you notice from the language down here, it says we're going to load the register RB with data from RAM at the address in RA. So register A is being enabled, and we're addressing memory by setting it into the memory address register. Then in step 5, we will take and enable RAM and set reg B, and that's it. There's no step 6. For a store instruction, we do the same exact thing in step 4. We take the address that's in reg A and set it into the memory address register, but then this time we do opposite. We enable the register and set it into RAM. That's load and store instructions. Now we have the data instruction. which is 010 opcode out of the decoder here. This is a 2-byte instruction where the first byte is the instruction and the second byte is the data to be put into a register. Look at down here at the bottom right, it tells you, it shows you the bits and how they're significant. And this instruction is only concerned with the reg B. There's no reg A. These two actually, reg A bits here, they don't mean anything. So you can put whatever you want right here. The decoder or the control unit will not do anything different based on reg A. So in step 4, what we do is the same thing as in step 1. We increment the instruction address register because after the fetch cycle, after step 3, the instruction address register is pointing to this next byte in RAM already. So we're going to grab that in a second, but first what we're going to do in step 4 is we're going to increment the instruction address register and set that into the memory address register, right? And then in step 5, we're going to enable RAM and put that data that we're pointing to, the next byte, and put it into reg B. So we've just loaded a particular 8 bits of data from RAM into reg B. Okay, jump register instruction. There's 3 different jump instructions. This one's specifically called jump register, and it only needs a step 4, and it only takes a register B, because it's simply just, we're going to take the contents that's in reg B, which is an address, and set that into the instruction address register for the next instruction cycle. That's simply all it does. There's no step 5 and 6. There is an address in reg B, and we load it into the instruction address register for the next instruction cycle. Now, jump instruction, this is similar to data in that it's a 2-byte instruction. But like the data instruction, the next byte in RAM was data. In this case, the next byte in RAM is an address that we want to jump to, right? So in step 4, we're going to enable the instruction address register and set it into the memory address register. So it will point to this byte in RAM. So now RAM is pointing to the next address right here. And then we will enable those contents onto the bus and put it back into the instruction address register. And that's how we jump to the next byte, to the next address in RAM. All right, let me talk about flags before we get to the next instruction. Is the jump if instruction. You can see from the processor we have a flags register, right? That's so we can set the value of the flags that get driven out of the ALU during ALU operations. So you might conduct an ALU operation, and then the next instruction we're going to check if any flags were set and then jump based on those flags. And so here we are. This is the jump if instruction. Yeah, this is a very, very busy slide. But you can see all the different jump ifs we have and the different combinations. Although some of these are not really feasible, right? Like some of them, like if we have jump to, I don't know, you might not have, it says jump to CA easy. I don't know what operation you might have where you will have the carry, the A larger than B, A is equal to B, and the Z flag set all at the same time. But you can check for that. You can check for any combinations of flags that you want using this instruction right here. So it uses the 4 flag bits to make the decision to execute to the next instruction address in RAM or jump to another RAM address to fetch the next instruction. So the idea, like I said, we want to execute an ALU instruction, then have one or more jump if instructions follow, and a jump if will jump or not depending on what happened during the ALU operation, right? Remember the 4 flags, we have CAEZ, carry out A larger equal A equal B and 0, and essentially we set up this instruction to check for the flag that we want. So we'll put a 1 in the value that we want to check for. So go up here to the top right. If we want to check for the carry flag only, then this will be a value of 1 0 0 0. If we want to check for the 0 flag only, it'll be 0 0 0 1. So here's an example right here. So here's our instruction. It's our jump if is 0 non-ALU instruction opcode of 101 for a jump if, and 0001, we're only checking for the 0 flag. This one, the next example, will check for the 2 middle flags, which is the A and the E. So this is essentially like checking if A is larger than or equal to B. We want to check if it's either one of those conditions, which is a condition that you check for a lot in software, right? If one value is larger, greater than or equal to another. So in step 4 of the jump if, it's the same as step 1. We are incrementing the instruction address register for the next instruction, and we are loading the instruction into the memory address register to point to the next byte in RAM. And so now in step 5, we enable the next instruction in the ACC and set into IAR, right? And so now step 6, if one of the tested flags happens, right? Looking at this over on the left, you can see the CAEZ AND gate. If we have a flag being driven in and one of our bits in the instruction, the last 4 bits, if it matches up, then we're going to get this OR gate activated. And then step 6, we're going to take and we're going to enable RAM, which is the address that we want to jump to, and set it into the instruction address register. If there are no flags, we will not jump. And the program will simply just, the instruction address register is already loaded after step 5 with the next byte in RAM after this jump address. So in step 6, if we test a flag, we're going to go to this byte in RAM that shows up here. If there is no flag tested, we're going to the next one, which is what's in the instruction address register. Clear flags. Okay, a couple more instructions, 110 and then 111. 110 is the clear flags. So you may want to clear flags because you may have a previous ALU operation that sets a flag, and you want to make sure that all the flags are clear before you do another ALU. There could be a flag set that you don't know about. So you want to go ahead and clear the flags before doing the next operation. So that's why you have a clear flags instruction. And the way the book explains to do it, it says right here in yellow, it says, no data is driven onto the bus, so operand ALU, or operand A of the ALU is all zeros, which in reality is not true, right? In physical reality, that's not true. It's a good idea, but in physical reality, the data bus will be high impedance. It'll be floating. It'll be tri-state. It won't be 0, right? The data bus is either driven to 0, driven to 1, or driven with a value, or it's floating. And in this case, if it's not being driven, it's going to be floating. So I've come up with a solution to make sure that we have a 0 on operand A to clear the flags. Because essentially what happens is we want to put 0 at A and 1 at B. So we're going to use bus 1 to enable 1 at B, and then I've created a bus 0 that's essentially like bus 1, but it's going to drive a 0 to operand A. So when you, and then the opcode is going to be 000, right? Because it's always 000 unless it's an ALU instruction and we're in step 5. So we're adding 0 and 1. And when you add 0 and 1, you get no flags. This is how we're clearing the flags. Is we're forcing the ALU to do an operation that outputs no flags. A is 0 and B is 1. A is not greater than B. A is not equal to B. There should be no carry, and the result will not be 0. We set those flags. We've just essentially cleared all our flags. Now, if you remember, this is what bus 1 looks like, right? If we put the bit high over here, this NOT gate will disable all these AND gates, and we'll get a 1 out of this OR gate. And so bus 0 is kind of the same way, except I got all AND gates here. I just kind of adapted that previous bus 1 and made a bus 0. But essentially, if we drive a 1 here, it's disabling all of these AND gates, and so the output will be 0. If we drive a 0 on bus 1, if bus 0 is turned off, not bus 1, bus 0 is turned off, then all of these AND gates will just enable whatever is on the input to propagate to the output. And so now this can assure that we can have a clear flags instruction. And this little box right here is essentially, I wanted to keep it clean on the last slide, but this is where bus 0 is going to be. It's going to be like in the data path of operand A of the ALU. And here is the first change to the control unit. Notice up on the top or the upper left over here, I've added the next AND gate number, which is A38 in hex, which is going to activate bus 0, and that is enabled from step 4, and also coming down to out of the 3x8 decoder, gate A16 will enable this gate along with step 4 to drive bus 0 at the same time we drive bus 1. Alright, now we're going to talk about the last part of the instructions, then we'll get into simulations, which is I/O. We have 4 I/O signals. Of course, we have the data bus, but you'll notice that the control unit has nothing to do with the data bus. But we do have that being outputted from the processor, and we have these 4 signals coming from the control unit, and these are I/O clock E, I/O clock S, data address, and input and output. And you'll notice that data/address, input/output is simply it's tied directly to the instruction register bits 4 and 5. So I actually made a change and put some gates here because the I/O instruction is only from the 3x8 decoder, instruction 111. I'll show you that in a little bit, but here we go with the instructions. The input-output wire determines the direction of data on the CPU bus, whether it's coming in to the processor or going out to other peripheral components within the computer system. And the data/address indicates if the bus is carrying data or an address to or from the peripheral. Peripherals are input-output devices that connect to the computer, such as keyboard, mouse, display screen, and others. I'll cover some of these in the next video after we complete the microprocessor. Clock E and clock S are used to set the registers outside of the CPU. That's I/O clock E and I/O clock S. So in step 4, for output, Reg B is enabled and I/O clock S activates the set signal. So we're enabling the contents of Reg B. It's traveling outside of the processor, and we're using the I/O set signal to set the value of Reg B in a peripheral outside of the processor, right? And so, well, I won't go through all of them. You can see down here, there's 4 different ways you can do it. You can do input address, input data, output address, or output data. That's it. And here's all the language down here. And in step 6, we don't do anything. We'll see more about this in the simulation. So here is the final draft of the control unit. This is what you should take a screenshot of. Well, you should take a screenshot of other parts of the control unit as well, so then you can crop it and print it off and then label the gates however you want. If you want to follow along and do this. But here's gate A38 for bus 0, which I already talked about earlier. Screen area is where you can improve it if you want. You can take these 2 AND gate, this AND gate and this NOT gate, and just make it one NAND gate. And then here's 2, I know it's crappy drawings, but here's a couple AND gates down here. I got A39 and A38. I'm tying the signal that's coming out of the 3x8 decoder for signal 111 in a non-ALU instruction. So I'm taking the wire that is A17 coming from, or A17 that's coming out of gate A17, and then just enabling the data address or input output with that signal and ending it with the instruction register instructions. So we don't have these signals communicating outside of the processor. They only do so during a non-ALU instruction. That is the I/O, which is decoder 111. Alright, so the main idea for the control unit, and this comes from the book, maybe this clears everything up, but the byte that is placed in the instruction register causes a certain activity to occur. Each possible instruction pattern causes a different activity. Each of the 256 possible codes represents a different specific activity. Right? That's essentially what the control unit does. Alright, now we'll get into the Verilog module, test bench, and simulation. What this slide shows is I was digging through the documentation for Icarus Verilog, and used to, in order to run a simulation that involves multiple modules. You see the control unit, right? I have a decoder 2x4. I have 3 of them actually, right? A decoder 3x8, the actual control unit, the test bench for the control unit, the clock gen, and the stepper. All of these Verilog files would have to be listed on your command line here in the first command, iverilog-o, your VVP, and then you would list all of these. But you can do it this way. You can create a .txt file that is the list of files, and on each line put a file name, and then you use this -c switch and the name of the text file, and it runs it. So you don't have to keep writing the command to putting all the commands on here. You write them in this file, and then you write this command that will go look in this text file for all of the included Verilog files that is needed in the simulation. And right, with no errors, you put in your VVP command control, the word you put here. This is a little bit different, this output, because I actually reset my PC and then I had to re-download Icarus Verilog, and I was using Icarus Verilog version 11, but now there's a version 12 that just came out a few months ago, probably like 6 months ago. And so now I'm using that, and it has this little finish call that, what is that, 1.2 whatever ticks, 1 picosecond. But then you just call your GTK wave and you're in. So now let's go look at the Verilog code. Alright, here I am in my Node++, where I type up all my modules. This is the control unit. It's called Control 2 because I did create another control unit months ago when I was first working on this, and I wanted to do it from scratch, so this is Control 2. But it is the control unit. And you'll see at the top I got the clock gen. There was no change to this file. Remember, the stepper was changed that I mentioned earlier in the video. This is it. I will also update all these and send these to GitHub repository for the project. Here's 2x4 decoder, simple decoder, right? 2 input select, you get 1 output bit lit. Here's the 3x8 decoder, you got a 3-bit select and 1 output bit lit based on the select value. Now here's control. I won't go through this real meticulously, but you can see here's the inputs up here. We just have the sys clock to drive the clock gen, which drives the stepper. I did implement a reset so we can synchronize the simulation a little better. And as a matter of fact, I'll talk about the reset more in the next video, but it only affects 2 pieces. It affects the stepper, which resets it back to step 1, and the instruction address register, setting the instruction back to 0 or in memory, right? But we have the 8-bit instruction, 4-bit flags coming in, and then all the outputs, all the set values for all the registers, memory address register, RAM, instruction register, instruction address register, the ALU accumulator, setting the flags, signal for the opcode, signal to drive bus 0, drive bus 1, also set TMP. Here's all the enables down here, and also with the IO signals right here. So just here's all the included modules I need. I have the stepper, the clock gen, 3 of the 2x4 decoders, and 1 of the 3x8 decoders, and just create wires that are needed to connect everything else up. And this is how I did it. I printed off that control unit paper, I set it next to me, and I started with the AND gates, and I just used Verilog primitives. Here's gate A1. If you look at your paper, you'll see that it's the enable for the instruction address register. That's the signal coming out. And what does it need going in? It needs clock E, and then it also needs from OR gate 06. So I just create a wire 06 that I'm going to need for this. Even though I haven't created the OR gate yet, I've created that wire, and anytime I create a brand new wire, just go back up to the top and make this wire. You can see the wires that I create or that I define up here in my wire definitions are basically in order of as I need them, as I'm plugging them into the AND gates, right? And the first AND gate wire I have is A28, which is A4, which is actually IO clock E. And I just go down through and connect each one. I mean, I used a magnifying glass because some of the areas on this paper, the lines are really close, but it actually works, and I'll show you. These are all the right signals. They're all connected in the right way. one thing I want to say, like I said, I didn't use the NAND gate, but here's a wire I called NA1 that if you were wanting to use the NAND gate, you would replace right down here, you would replace AND A21 and not gate N3 with just one NAND gate, right? If you wanted to do that, I am going to leave it the way it is. Also, you will replace this N3 with the NA1 signal output for gate A29. Yep. And then here's bus 0 output, the new gate A38, the new gates A39 and A3A for I/O, and then just tying in the instructions to the decoder inputs. Like I said, I'll put this on GitHub and you can check it out for yourself. But here's the simulation for it. Here's I did put a bunch of comments up here for what's supposed to happen, but what I essentially do is just create all the registers to drive the inputs to the control unit, create wires for all the outputs, connect them all together in the instantiation, right? I have this initial block here that I need for Icarus Verilog and GTK Wave with the dump file and the dump vars, system directives, create the clock, and now down here's the simulation. I go through each instruction. I go through the 8 ALU instructions, and then I go through non-ALU instructions, and then with some of the jump instructions, different scenarios based on flags. So we start with add. I'm going to start the sys clock at 0. Don't do anything with the flags yet till I need it. I'm going to implement the reset, and I'm going to wait complete 48 simulation ticks is how long one instruction cycle takes, because there's 6 steps, and then there's actually 8 ticks of the sys clock, ticks being from negative to positive and positive to negative. So we have 48 simulation ticks for an entire instruction cycle. And I go through, and right here's where the actual add instruction gets carried out. Then I go to shift left, shift right, a not, and I'm just rotating the registers. So I got, first I start off with R0 and R1, then R1, R2, R2, R3, R3, R4, and so on, back to R0, R1, but I'm doing shift left, right, not, and, or, XOR, and compare. All the ALU instructions right here we're testing. Then we get into the non-ALU instructions. We'll start with a load, we'll do a store, we'll do a data instruction, jump register, and then a jump to the next byte in RAM. And then here's special case for a bunch of different jump ifs, right? I'll go ahead and bring in the flags. So I'm setting the flags right here for A and E, and then I'm right here, I'm testing for, well, the flags are originally set at 0, 0, 0, and I'm testing for the carryout flag. In this case, no jump should occur. Then I'm going to set the flags to 0, 1, 1, 0. I'm going to test for the A, so a jump should occur here. I'm going to test for the E, jump should occur here. Change the flags to 1, 0, 0, 1. I'm going to check for the Z flag. A jump should occur. Now I'm checking for A is greater than or equal to B. No jump should occur here because the flags are C and Z, not A and E. And then this I'm checking for both C and Z, and it should jump here. Then after the jump ifs, then we have the clear flags instruction, so we'll check the operation of that. And then the 4 different I/O operations at the end. Here's that file list I was talking about. Now let me take you back to the simulation. Alright, I decided to do this in PowerPoint slides instead of showing you actual GTK Wave because, well, it acts kind of wonky. This is much better, and this is the full simulation of the control unit. I did have some bugs to work out at first. I worked them out, and now there's no red on the simulation, which is great. It's all green, which is good. And I'll go through each. We'll go through each operation I just talked about. So at first, the simulation, right? The reset is enabled. Oh, I'll also take out some of these clock signals and make it to where it's a little bit cleaner and easier for us to read as we go along. So now taking out all the clock signals here, you can see it's not so crunched up. But the reset is started here. It's enabled, right? So it's just continuously in step 1. It's enabling the clock E and the clock S in step 1 and bus 1, right? The reset is done here. Now I'll start with the actual instruction, which is the add instruction, and this is the fetch part of it, right? Steps 1, 2, and 3 is fetch. For every single instruction, it does the same exact thing. So I'm only going to cover the fetch part one time. And so right here in step 1, we have the fetch. And what it does is you look at the values over here. Bus 1 is 1. We are enabling the instruction address register. We are setting that address into the memory address register. And then we are setting the value in the accumulator because we are adding 1 to the address, right? And this is essentially what happens in the processor, right? We are enabling the instruction address register, which puts the address out onto the data bus. It's present at operand A at the ALU. It's also present for the address for the memory address register. We have a signal that sets that address in the memory address register. We also have a signal that activates or enables bus 1. So now we have our current instruction address at operand A of the ALU, and we have 1 at operand B. Our opcode is 000, and we know why. And we're setting that value into the ACC. So we've just incremented the address by 1 to point to the next instruction in RAM for the next instruction cycle. Now step 2, what do? We enable the contents of RAM that we just addressed, and we set those in the instruction register. This is what happens here, right? Step 1, we address RAM. Now we're enabling the contents of that address of RAM out onto the data bus, and we're setting it into the instruction register because that's the next instruction we want. And then finally in step 3, we have to update the instruction address register with the +1 address that we stored in the accumulator. So we're enabling the accumulator and setting it into the instruction address register, which is demonstrated here. Just enable the next address that's an accumulator out onto the data bus, and we will set it into the instruction address register. Now we get into ALU instructions. So the first one was add, right? And how you can always tell is look at this little box up here. You can read the instruction, right? The instruction, the first bit is a 1, so it's ALU instruction. The next 3 bits are 000, so it's an add, right? And then the next 2 bits from that is register A, and then the next 2 bits is register B. So by looking at this instruction, we can tell it's an ALU operation, which is an add, and we're dealing with register 0 and register 1. The opcode is also shows up right here, but you know it's not driven until step 5, and in this case, in step 5, it'll still be 000. But in step 4, what do? We take the contents of R1, which is our register B, and we set it into the temporary register, right? We've enabled R1, which is our operand B, and we set it into the temp register with this set signal, right? Now in step 5, this is when the opcode is driven, but like I said, it's an add, so it's still driving 000, which you can read up here at the top. But what do here? We take and we enable R0, which is our RA, and we set the accumulator, the result, the ALU result, into the accumulator, and we also set flags in case there were any flags that were generated on this ALU instruction, right? So we're enabling operand A out of R0 to go into ALU operand B. Temp doesn't need to be enabled, right? It's a byte. It's not a register, so it only has a set, and it never needs to be turned off, so it's always driven. And if bus 1 is not enabled, then the value of TMP propagates through operand B of the ALU. So we have operands A and B, then we set the value in the accumulator, and we also set the flags. And now step 6 is, as long as it's not a compare operation, we want to take the result, which is in the ACC. So we'll enable the ACC, and we will set it into register 1, which is our RB from our instruction, right? So we are enabling the contents of the accumulator. It'll be driven onto the data bus. It'll be inputted here at R1, where we will set it back into R1. And that is how we just did, and how the processor just did an add operation. Now we're going to go through the shift right, which takes, in shift right, it takes operand A and puts the shifted value into, not operand A, reg A, and takes the the shifted value of reg A and puts it in reg B. And if you look at the instructions at the top here, you can see RA is R1 and RB is R2, the binary values of 1 and 2. So in step 4, now this might not make sense because in a shift left, shift right, or not, we're only dealing with operand A. But the control unit will still take the value of operand B and set it into the temp. Although it's not going to matter, it's kind of a wasted move, but it would take more logic gates to prevent this from happening than just allowing it to happen. It's in step 4 for shift right, shift left, and not, it doesn't really matter. It still happens, but it doesn't matter. And like I said, it takes more logic gates to prevent it from happening. So we just allow it to happen. So in step 5, we actually get what we want to happen. We are going to enable RA, which is R1 in this case. We are going to set the ACC. We're also going to drive the opcode. Notice the opcode changed to 001. In step 5, we're driving the shift right opcode with presenting RA, which is R1, at operand A of the ALU, and we're setting the value in the accumulator, and we're also setting any flags in case there's any carryouts from the shift, right? And then in step 6, we will take that value from the accumulator and put it in back into reg B, which is R2 in this case. Shift left does the same thing. This time where reg A is R2 and reg B is R3. Another wasted step here, doesn't matter, but we don't care about it. Step 5, we're actually doing the ALU operation. Notice the opcode is actually shift left opcode now. We're capturing the value in the from R2, which is our RA, in the accumulator, and we're setting flags. And then in step 6, we're taking the value that's in the accumulator and setting it back into reg B, which is R3 in this case. A not does the same thing right here. We don't care about step 4 for the not. It happens. It doesn't matter. Step 5 is where we're actually doing it. Notice the doing the ALU operation. Notice the opcode up here, 011. So we are enabling reg 3, which is RA, setting the accumulator, setting flags. Step 6, we are putting that into reg B, which is R0 in this case. If you look at the instruction, the last 2 bits are 00, which means reg B is 00, and we are actually setting R0, which is good. Now let's get on to the AND, which is actually this. We go back to like the add. We're operating on 2 operands, so we do need the reg B to be set into the temp register, which happens in step 4. Then step 5. Notice the opcode, it's 100, it's the AND, and we are taking reg A, which is R0, and now we have the temp, which is operand B, and we are setting the accumulator and setting flags. Then we are taking the accumulator value and setting it back into reg B, which is R1. Now we have an OR, which does the same exact thing. It takes operand B, set it into the temp. Then we drive the opcode, which is an OR 101. We take reg A, we set the ACC, and we also set any flags. And then we take the value from the ACC and set it back into reg B, which is R2. And same thing with XOR. We take operand B, set it into the temp. Then we drive the opcode, which is 110 for XOR. We drive the value that's in RA, which is R2 in this case. We perform the ALU operation, we set the value in the ACC, and we also set any flags. Then we take that value from the ACC and put it back into reg B, which is R3 in this case. Now we come to a compare operation, which we're just comparing A and B. So the first thing we need to do is take register B, which from the instruction is R0. Yep, so we're taking and enabling R0 and putting it in the temp. Then we're sending the opcode, which is 111. We're taking reg A, which is register 3 in this case, enabling it to operand A of the ALU, capturing the ALU result in the ACC, setting the flags. And then in step 6, notice there is no step 6 because it's a compare operation, right? We don't care about the result, so we're not going to take the result from the ACC and put it in reg B. We only use the compare operation to set flags, right? Now let's go to non-ALU instructions. The first one is load. We're loading R2, R3. So remember on the load and store instructions, we're loading a value from RAM at address in R2 and putting it in R3. So in step 4, what happens? We take R2, which is our RA in this case, and we're setting it in the memory address register, right? RA, or R2 in this case, carries the address that we want to load from RAM. And then in step 5, we actually, here's a breakdown of step 4, right? We are enabling register 2, which is an address, and we're setting it into the memory address register. Then in step 5, we're taking the RAM, the value that's in RAM that we just addressed, and we are setting it into R3, right? So we will enable the value in RAM, it'll be on the data bus, and then R3, we'll set it in R3. So we've just loaded data from RAM into a register. The store does kind of the opposite, right? It loads data from a register and stores it into RAM. It doesn't load, it stores it into RAM. So what we'll do is we'll do the same thing here, but we're dealing with R0 and R1 if you look at the instruction, 00 and 01. So we'll take RA, which is the address, and R0, and we will set it into the memory address register. And then in step 6, we will take and enable the value in R1, which is our reg B, and we will set it into RAM at the address that we just addressed in the previous step. So we just store data from register into RAM location. Here's data. Put this little graphic here so we can kind of remember what happens. But in step 4, it's the same as step 1 because the instruction address register is already pointing to the next byte in RAM. So we need to put that in the memory address register and then increment the address again to the next byte. And then in step 5, we will take and we will enable the data in RAM and set it into R2. And then in step 6, we will take the accumulator value, which is the address, the incremented address, and set it back into the instruction address register for the next instruction. Here's the jump register. Remember, it just needs step 4, simple instruction. The address is in RB. And in this case, RB is register 00. So we're enabling register 0, and we are setting it into the instruction address register. So we're just the next instruction cycle will simply jump to the address in RAM that was located in RB. We're jumping to the address in a register, jump register. And now the jump instruction, we enable in step 4, we enable the instruction address register, and we set that into the MAR. So we're going to the next instruction in RAM, and we're taking that RAM address, the address that's in RAM, the next instruction, and loading it into the instruction register for instruction address register for the next instruction cycle. Okay, we got a bunch of jump ifs going on here. Notice the flags up here, 000. We shouldn't jump. All right, if we did jump, there would be a step 6. In this case, this was the first case. Look at the instruction. We're testing for the carry flag. So because we got 1000 in the instruction, there are no flags lit. So therefore, in step 4, we are doing what we do to increment. In step 5 is where we make the actual check. Step 5 is where we increment. We take an increment for the next address by taking ACC and put it in the instruction address register. But then the flag that we tested for is not there, so there's no step 6 and we don't jump. This time we are going to jump though, so you notice there is a step 6 over here because we're checking for the A flag. And the flags that are set are A and E. And so we're going to check for the A flag and it's going to be enabled. And so we'll do step 4. Does the same thing as step 1, increments the address register, increments the memory address register. We're going to set up the address register for the next instruction, but now we're going to actually rewrite over it because we are going to jump. If you notice in step 5 and step 6, we're setting the instruction address register. So we're setting it to the next instruction in step 5. But if we test a flag, we're going to overwrite it right away from the contents in RAM because now we're jumping. And so the same thing happens here. We are testing for the E flag, and the A and E flag is set, so we will jump. There's step 5, step 6, we jump. Again, here we have a flag. We have the 0. We're testing for the 0 flag, and the flags have a C and the Z flag set, so we should jump here. Now we are testing for A and E, but the flags are C and Z, so there's no step 6 after this step 5, right? We won't jump. Another jump if scenario. Probably too many in here, but it's cool. We'll zip through them. We are jumping in step 6 here, because we're checking for C and Z, and we do have the C and Z flags. Now we go into the clear flags. Remember I made that change with bus 0. So you can see bus 0 is lit and bus 1 is lit. So now and then the opcode, of course, driving to the ALU is 000. We're setting the flags. We've just cleared the flags. It only requires one step. Now we get to the IO instructions. There is something a little bit confusing in this one here that I'll figure out later and talk about in the next video, but it is working. It's just, so for this instruction we have 0000, which means we are inputting data and we're using register 0. So, but if you notice, the clock E is for enabling data outside of the processor to come in, and clock S is for enabling data to be set outside of the processor. But if you notice in step 4 here, it's as if we're outputting, because clock S is setting outside of the processor the contents of register 0, which if the peripheral isn't paying attention to this, no problem. But it's kind of like a wasted step, like before with the single operand ALU instruction. And right here in step 5 is where the actual money is made. We're inputting the data, right? Because we're inputting so we're actually setting data from the data bus into R0, and we're enabling whatever peripheral that's coming from outside of the processor and setting it into R0. So this is inputting data. And inputting address does the same thing. It's got this kind of wasted operation. And then in step 5, we set the address this time into R1, because that's what RB is in the instruction. And so now we are outputting data, and now this one actually works correctly because it just has one step. We simply output the data from R2 and set it into whatever peripheral is listening outside of the processor. We also notice the IO lines at the bottom here are actually activating now, whereas before they weren't, and that's due to the 2 new AND gates I put in there. And then here's outputting an address. Same thing, we just need to output from register 3. We are telling the peripheral that it's an address by this bottom signal here. Address is 1. It is an output, and go ahead and set it when this set tick happens from the data of R3. And with that, we have completely verified the control unit. All the signals, all the conducting going on, it all works properly. The next video, we will complete the processor by creating all of these general purpose registers: the instruction register, instruction address register, flags register, accumulator, the TMP register, bus 1 and bus 0, and putting it all together in a processor. Stay tuned. Next video. Thanks for watching this one. I know it was long, but there was a lot of information. I hope you understand what the control unit is about, what needs to happen, and also the instruction set. As always, thanks for watching. Have a great day.